what we have seen in the previous lectures was how to calculate the Fourier coefficients of a given periodic waveform, and through an example we saw how this information could be utilized to assess the steady state performance of an electrical network excited by periodic non-sinusoidal sources. Today we'll take up the concept of frequency spectra. To introduce this, let us consider the statement of a periodic function of time. Suppose I describe the periodic function of time as follows: period is T0 and Ft equals A for T ranging from 0 to T0 upon 2 and minus A for T ranging from T0 by 2 to T0. This is a complete description of the periodic function, but this is just a cold statement of facts. On the other hand, if I picture this information in the form of a waveform, then the whole situation comes alive. So if you plot this for a whole period, you have this and repeats itself endlessly in both directions. This is A, this is minus A, 0, T0 upon 2, T0, and this is of T. So information about the periodic waveform presented in this manner gives you a real feel for the variation, and it is often useful therefore for us to plot these functions of time through waveforms like this. We know this is called a waveform. And that is the reason why an oscilloscope is such a useful instrument in the laboratory, because we can see the variations with respect to time which are often masked in an analytical expression of this type. Now, when you perform the Fourier analysis of this, we can describe the Fourier coefficients of this waveform. We know that Cn, the Fourier coefficient in the exponential representation, is minus j 2a by n pi. You recall that in the trigonometric expansion of this function of time, the coefficients of sin n omega naught t is 4a by n pi, and since Cn is an minus j bn by 2, bn terms are only present 4a by n pi for odd n, therefore Cn will be minus j 2a by n pi for odd n and 0 for even n. Now this statement again gives you the complete picture, but there is nothing like representing them in the form of a figure. So suppose we want to do a similar operation like this with respect to functions of time. So we should be able to plot Cn for different values of n in the form of a graph or a figure. But then there is a problem. Cn is a complex number, so if we have to indicate a complex number, we have to indicate both its magnitude and phase. There are two parameters associated with each value of Cn. Therefore, a convenient way of doing this would be to plot the magnitudes of Cn for different values of n and the angle associated with Cn, with angle associated with Cn, which we call phi n, for different values of n. So in this case, we can graduate the x-axis in terms of n or omega naught. Suppose you do it in terms of n, 0, 1, 2, 3, 4, 5, etc. And on the negative side minus 1, minus 2, minus 3, minus 4, minus 5, etc. So when you plot the magnitude of Cn, then you have, there is no DC term, there is one component here, another component here, third component here. This is even harmonics are absent, therefore that will be how it looks like. And phase, every non-vanishing Cn will have minus 90 degrees, as you can see here. Therefore, and since for minus n it's the conjugate, you have plus p by 2. Minus pi by 2. You can graduate this x-axis not necessarily in terms of n, we can as well do it in terms of frequency or angular frequency. So I can write this as 0, omega naught, 2 omega naught, 3 omega naught, and 4 omega naught, 5 omega naught, etc. The point to note is that this is what is called a line spectrum. This such a representation is called a spectrum. This is called the magnitude spectrum. And this is called the phase spectrum. And together they go by the name spectra, the magnitude and phase spectra. One point we should note is that as long as the function is periodic, that is the type of functions we are dealing with at this stage, the spectrum consists of components only at the DC and possible integral multiples of the fundamental frequency. There cannot be any term in between. So these are called line spectra. Both this magnitude and phase spectra are now for a periodic situation are line spectra. And the spacing between two adjacent components, this is also a component but 0 magnitude, the spacing between two adjacent components is omega naught if you graduate this in terms of frequency. So the entire information regarding Cn can be pictorially represented in this fashion. It gives you in a graphic way what are the frequency components present and what are the relative sizes. All this information is given in a pictorial representation like this. Therefore, it is often convenient and useful for us to plot the spectra of periodic waveforms in this fashion. For example, you draw an envelope like this, you can say this is how various Fourier coefficients decay for large values of m. So generalizing this, we can say now that for periodic waveforms we have two kinds of spectra, the magnitude spectrum which is really a plot of the magnitude Cn as a function of n or omega naught or omega, and so in general you have values for integral values of n or integral multiples of omega naught. You may be a little puzzled about this meaning of minus omega naught. What is the negative frequency? It is just the coefficient of the term t in the exponential representation. You write minus j omega naught t. It has the dimensions of frequency. As I mentioned earlier, these two together constitute a sinusoid of frequency omega naught. So this is only a mathematical terminology that we use, and we should leave it at that. We should not try to find out a physical meaning for minus omega naught as a frequency. If you plot the phase spectrum, in general again you have some values. This is the angle of Cn, which is equal to Pn. The phase spectrum turns out to be an odd function of n. Why? Because we observed earlier that Cn, C minus n is Cn conjugate, which means that the angle associated with Cn and the angle associated with C of minus n are the negatives of each other. Therefore, if for n equals 2 it has a certain phase angle, n equals minus 2 it is exactly the negative. So the phase spectrum is an odd function of n. On the other hand, the magnitude spectrum, which is the magnitude of Cn, is an even function because the magnitude of C minus n is the same as the magnitude of Cn. So a magnitude spectrum is an even function of n. This is an odd function of n. So these are two important properties of the spectra. The magnitude spectrum is an even function of n, the phase spectrum is an odd function of n. And it is conventional to plot the spectra for both the positive and negative indices n, even though, as you can see, if we give this information pertaining to positive n for Cn and positive n for Pn, we can reproduce what is happening on the negative side utilizing the property of evenness for the magnitude and odd for recognizing that Pn is an odd function of n. It is also sometimes this is also done. Instead of plotting Cn, one plots square root of an squared plus bn squared, this being the amplitude of the nth harmonic component. You recall that in the trigonometric expansion of a function of time, we can the amplitude of the nth harmonic is square root of an squared plus bn squared. And this is the coefficient of cos n omega naught t plus phi n function of time. So this can be plotted also 0, 1, 2, 3, 4, etc. This is a single sided sometimes called amplitude spectrum. Because what we are really plotting is the coefficient in the you recall that the nth harmonic is represented by cos n omega naught t. So we are plotting this as an alternative. So instead of this magnitude spectrum, one can plot this, but in this case we only have a positive non-negative values of n to deal with. Therefore, this turns out to be a single-sided amplitude spectrum. This is an alternative way of plotting the magnitude spectrum, nothing more than this. However, we normally confine our work to utilizing plotting the spectra in this manner rather than in this manner, because that will be convenient for us when we go to the Fourier integral concept. You notice that if this is C0, this is C1, this is C2, when you go to the amplitude spectrum, square root of an squared plus bn squared, as you know, is 2 times C of n. Therefore, this will be 2C1, 2C2, 2C3, etc. But the DC term will be the same, that is C0. Okay? So, the concept of spectra is just a way of indicating the various harmonic coefficients in a pictorial way, and since each harmonic coefficient is associated with two quantities, either an or bn, or magnitude of Cn and phase of Cn. For example, if you choose to plot in this fashion, the angle information is again once again this. So, as far as the phase spectrum is concerned, you do not have any alternative. On the other hand, if you like, you can plot an and bn separately, but that is an unconventional way of doing it. So, since each Fourier coefficient is specified by two parameters, we need to have two spectra, and usually we do this in the form of a magnitude spectrum and a phase spectrum.